A quick note about the proofs that I'm doing in this section. Remember, this section here is all about proving and using those set equivalences that are at the start of the first video of this topic. But the proofs I'm doing, I'm kind of cheating a little bit. So the proofs cheat a little bit, and let me tell you how. For example, when we were showing that A union B intersect A union C, when we're showing that was a subset of A union B intersect C, the first thing we did is we said, let X be an element of this guy. Let's call that L for the left-hand side. But that's assuming that this actually has some elements in it. Maybe it's empty. Let me give you an example of a situation where this would be empty. Well, maybe A is indeed the empty set itself. Maybe B is the set 1, 2, 3. And maybe C is the set 4, 5, 6. Just an example. In this situation, if you calculate this, you'll find that this whole thing is the empty set. So we can't actually take an element out of it because there are none. So I'm kind of leaving that case just in the interest of brevity and clarity. But it is possible that some of these sets are the empty set. And if you were to do this proof 100% airtight, you would have to take that case into consideration at all. So maybe this would be case 1, where L isn't the empty set, and we did what we did. And then case 2, we'd say something along the lines of L is the empty set. And it's a short case. Well, if L is the empty set, then of course, clearly, since it's the empty set and it's a subset of everything, we know that the empty set is a subset of, I'm going to call this the right-hand side, R, subset of R. So there might be a few situations where I'm not being particularly careful with empty sets, but just know that going forward and looking at those proofs, there are cases where I'm not taking the possibility of it being the empty set into consideration, but to do it totally airtight, I would have to. So in summary, the proofs in the videos for topic 19, whenever a set is mentioned, even a combination of sets, it is assumed non-empty. But all of these results will hold for anything that is empty as well. It's just a few extra complications in our proof.